So anyway, a warm welcome also from my side to this symposium. And yes, in the last 2 years, we learned a lot what works, that a lot of things work with online sessions, but we also learned that not everything works. So I think the symposium, SFTE symposium, is one of the things that does not work. However, we make the best out of it. I would like to thank the organizers of this event, so that at least this online version is possible. Thank you very much. And I would also like to thank the presenters that took on the task of having a presentation without seeing the audience, which is not that easy. I see that at the moment. Anyway, I'm looking forward to interesting presentations and I hope that to interesting thoughts. When I saw this year's symposium's motto, my thought was, well, not again, please. Why shall we think again about reducing flight test cost? I mean, we have program managers for that and controllers. Why not talk about doing the job properly? Then I thought about the reasons why we are constantly challenged to try and reduce the flight test part of the flight test cost of aircraft development. Not that it can even be worse. I know a company in which flight test essentially was considered as superfluous by the boss. The designers, especially he himself, were so good that checking their designs basically meant insulting them personally. Flight test was tolerated only as a necessary evil required by annoying regulations. Finding something unacceptable during flight test probably was not very popular in this company.
Rudolf, just for information, we don't see your slides anymore.
Okay. So they're back here now?
Not yet, I'm afraid. We have a blank screen. In fact, we see part of your desktop.
Yeah, okay. Just a minute. Click.
Yep, that's good again now, Rudolf.
Okay, so now you see the presentation and nothing else, right?
Correct.
Oh, well. Okay, it's going to be interesting. Anyway, what I was saying was that there is several points to see flight test, and there are extreme points for that. Anyway, I think the approach to cut the cost of flight test is not something unfamiliar to this audience. Flight test obviously is expensive, and it ties up a lot of highly specialized personnel and requires pricey facilities. Therefore, the desire to reduce that cost factor is understandable and essentially not different from the efforts for cost reductions in all other steps of the development cycles. And there is one peculiarity of flight test that puts the attention on our field. Flight test is the development step that starts last. So we are late by definition. Completion dates of a program tend to stay as fixed as possible, but when flight tests start, it's very hard to ignore any previous delay any longer. And while sometimes there are development cycles included in the planning to allow fixes for finding in flight test, all too often the steps do not work out as originally planned because of earlier delays. We all know situations where the window of opportunity for fixing flight test findings has closed even before flight test started, because the planned starting date of the fixed cycle was not adapted to the delays piled up over time. Now, how did we come to the present status with respect to what we do, test in flight, and how we do it? For that, I would like to go through aviation history with a personal view in flight testing. The very first time mankind raced into the air, the first flight testers start their work. Little did they know about their endeavor, and the most important goal of any flight was to come down unhurt to fly another day. The rise of knowledge was large, but much larger was the area of the unknown. With the gained experience, aircraft became larger, faster, more sturdy and reliable, and as a result, more useful. World War I gave aviation a big development push. Development of manufacturing of aircraft became a large business, and among the special trades created for the business, the flight testers evolved, as a pilot first and trained on the job. Over time, these flight testers developed a sense of what is desirable when flying an airplane. The first rule set for aircraft certification was published in 1919, and from then on, not only a potential customer had to be convinced of the merits of an aircraft design, but also a certification authority. The time until the end of World War II again saw tremendous progress. Range, speed, capacity, and capability of the aircraft increased. Between the wars, air travel became routine. The capability of aircraft for the military expanded. Obviously, this was the result of more knowledge and experience gained during former projects. To expand capability, new equipment was added to the aircraft, allowing, for example, flying in bad weather and at high altitude. This new equipment increased the complexity of the aircraft, and it had to be tested too. Methods to increase strength of structures without adding weight were developed. They also had to be tested in flight to complement ground tests and validate calculation methods. Flight test answered with the use of sophisticated measuring and recording equipment to gain detailed insight also in dynamic processes. Test flying became a systematic activity, its development pioneered by national bodies like, for example, the British Royal Aircraft Establishment and the US-American NACA. Standard maneuvers to evaluate aircraft characteristics were invented and refined. After World War II, there was no slowdown. On the military side, an immense number of jet combat aircraft types came to the air forces, sometimes serving just a few years before being replaced by a successor. Supersonic flight became ubiquitous. All-weather capabilities started to evolve, all adding again to complexity of the aircraft system. The helicopter started to come of age in the civil and military worlds, duplicating the development of the fixed wing in increasing performance and complexity. Civil fixed-wing aircraft saw further development, faster, higher, further, first and foremost driven by the transition to jet propulsion. Air travel became commonplace. The higher performance was possible again because of better knowledge of all areas. Systematic research, knowledge in aerodynamics, flight dynamics, material data, structure, calculation methods, and so on was assembled. And partly by flight research projects like the X-planes. But again, new unknowns were encountered, for example, the material fatigue issues that plagued, for example, the early Comet aircraft after the flight test phase. Innovative test methods on ground and in flight had to be invented to address those unknowns. Flight test became an own branch of the industry. The large test pilot schools were founded and took over the vital role in training the testers and accumulating and teaching the tribal knowledge of flight test. The understanding that flight test is a team effort finally prevailed, ending therefore the heroic age of flight test as an endeavor of the lone, death-defying test pilot. Because of more and more capable instrumentation, the insight in what was happening in flight increased constantly. When looking back at the 50s and 60s, it's hard to believe how projects like the X-15 or the Concorde could be started with so many unknowns. But they and a lot of others were started and came to a successful completion, adding again to the knowledge and experience of aviation. An important thing we have to put into this time is the start of a flight safety culture. The accidents rates, especially in military aviation, were shockingly high, and in flight test was even higher. Systematic research to identify the common reasons of accident was started, leading to efforts like establishing of flight safety organizations, standardized training, systematic accident investigations, publications of lessons learned, and others. Approaches, methods, and tools that are commonplace to us nowadays. In the 70s and 80s, two trends that would change aviation industry became apparent. Fuel became more expensive, and the Cold War came to an end. Money for the military was getting scarce. Those trends, together with the fact that somehow there was more and more effort necessary to improve the flight performance, led to an end of the faster, higher, further. New aircraft did not necessarily fly faster or with higher payload, but did the same as their predecessors, but with less fuel. The military did put more and more emphasis on multi-role aircraft, jacks of all trades with an ever-growing span of capability. The aircraft design became more optimized and even more complex. Besides other topics, the user interface moved into focus of the designers and operators so that these all-rounders could also be handled by the air crews to bring all capabilities to bear. Stealth designs were introduced. Flight test learned how to handle the complexity. Because of more sophisticated design methods using ever-increasing computer power, the flight test philosophy somehow changed. Data of flight test was used to validate the results of calculations, test on ground facilities, and simulations. More sophisticated flight test instrumentation systems recorded large amounts of flight data. The handling, distribution, and analysis of this data started to take more importance in the flight test organization. With the addition of more equipment to the aircraft, the scope of flight tests grew wider and wider. Flight test nowadays is composed of many subdivisions. The demand for specialized training for flight testers became big enough to allow the foundation of civil test pilot schools. The new as well as the established flight test schools added system testing phases to their syllabuses to teach this aspect of testing to their students. But all the new facets of flight testing were only complementing the more traditional activities. The knowledge how to put an aircraft through its paces, for example, during handling qualities and performance testing, still was and is essential. In recent years, some new challenges have reached flight test. UAVs, while having been around a long time, came to age. And in the civil aviation, the environmental aspect has reached tremendous significance. A lot of research, including flight test, is done to fine-tune conventional designs and to test the real potential of new approaches to aerodynamic shapes and propulsion. In the military, the individual aircraft, while still growing in single-ship capability and versatility, is getting connected, thus having a higher level of system testing in the portfolio of the flight test organizations. On the other hand, the number of new aircraft development projects is constantly decreasing, especially on the military side. This brings new challenges to the flight test community. Now, that retrospect is necessarily based on my experience and interests, but I'm sure I'm not the only one who is flashed about a tremendous progress in aircraft development over the short period of about 120 years since the first powered flight. Now let's come back to this symposium's motto and try to extract some numbers from history to understand and further discuss the desire to reduce flight test. For that, I tried to gather data on the duration of flight test phases over the years. The data sometimes is questionable, and when comparing them, there is a lot of room for discussions. Each project has its own circumstances and constraints, but I think in the end, the data is good enough to draw some conclusions. Now, on this graph, you can see the duration of flight test programs. I define it as the time between first flight and introduction into service. And the graph covers civil transport aircraft. On the horizontal axis, you see the date of the first flight, and then the vertical axis shows the duration of the flight test phase in years. There are some outliers, especially the Concorde over here, that still is unique. But in general, you can see that flight test of civil transport aircraft usually is done in between 1 and 1.5 years until the mid-90s. And there is a small but constant trend to longer flight test phases. But since the mid-90s, the duration of flight test phases has about doubled. In the military area, the picture looks slightly different. Flight test programs on average took much longer than in the civil airliner world. And the variation on the duration between programs is much larger, depicted here with a maximum and a minimum trend line. The increase in flight test phase length over the years is more distinctly than in the civil transport area. And in this graph, the trend to increase starts again, the same trend to longer durations can be seen starting in the mid-90s. Here, basically, in the form that the average curve is joining the maximum curve value. There exists a lot of reasons for the difference between military and civil projects. I don't want to discuss them in detail, but rather point out the commonalities of the two pictures. Both show a trend towards longer flight test programs over time, and both show a change starting in the mid-90s. While I think this is an interesting observation, I'm afraid that at the moment we do not have enough data for a close analysis of this effect. So let's concentrate on the increase of flight test duration over years. But before I want to do that, let me discuss another issue that can be seen on these graphs, and that I mentioned it before, has a large influence on the way we do flight test. If you look at the pure number of aircraft projects, you see that the time between new projects also has increased constantly. While in the 50s and 60s, a brand new aircraft program was started every few years or even faster in the military world. Nowadays, especially in military aircraft development, an engineer must be lucky to get the chance to see more than one project in his working life. There is a good chance that the flight test engineer will only participate in one first flight phase of a large aircraft development project during his career. Aircraft nowadays have a long service life. Military aircraft often are replaced by new variants of the same type with extensive upgrades in mission suits, but only minor changes in other systems. The result of that is an uneven distribution of work between the flight test disciplines. Avionics systems are constantly updated. Basic systems like flight controls, electrical power generation, fuel or propulsion usually have much longer update intervals, and the structure usually solves the purpose quite well for decades. Examples being the F4 Phantom, still in service in some nations 63 years after the first flight, and Eternal B-52, that according last plans of the US Air Force will be in service for more than 100 years, structurally almost unchanged. In the civil area, this effect is not so significant since old aircraft are not retired because of capability shortcoming, because of efficiency and fuel efficiency issues.
Rudolf, I'm sorry to interrupt you, but we lost your slides again.
Okay. Sorry. Do you see nothing at all?
I guess we see your desktop. I can see your taskbar and your icons. So I'm sure we are seeing something from your computer, but not the presentation, unfortunately.
So now you see the presentation, and now you should see again the slide.
Perfect.
So I hope now I have repaired this issue completely, but we'll see. So, yes, I was talking about the interval of flight test programs and the possible influence on our flight test operations. And I will come back later on some of the consequences for us. But now let's go back for the moment to the test program duration topic. To get a grip on this development, let us have a look on what drives the effort for flight test. Flight test serves two purposes: to ensure that a design works as desired by its designers, and to create evidence to show compliance with certification and customer requirements. More requests by designers are usually created when they develop systems that are more complex or are getting away from the traditional solutions. More complexity usually will result in more development cycles to fly, fix, fly. Innovative systems or approaches to design have to be complemented by a more cautious flight test pace to build up experience. An example: when using new ways of structural optimizing, the underlying assumptions and the behavior of the design have to be validated in flight. Airworthiness regulations are including paragraphs that have to be verified partly or completely by flight test. Nothing unknown to this audience, but over time more and more such paragraphs were added, partly because of lessons learned from accidents and incidents, and partly to cover additional types of equipment and modes of operations. I think it's fair to say that regulations tend to become more voluminous over time. The old requirements stay, the new ones are added, therefore expanding the flight test programs. Now, customer requirements are subject of contract between customer and aircraft manufacturer. It's normal that a customer wants improved performance or capabilities in a new project, in a new product, and that he wants a proof of this requirement, very often based on flight data. And the more, I think it's a good summary to say that more flight test is needed when aircraft are getting more complex, the regulations getting more voluminous, customer requirements more extensive. Again, this should come to no surprise to this audience. I think we can agree that the complexity of military aircraft as well as airliners have increased considerably during the 70 years I cover with my survey. The same is true for the volume of regulations, and especially in the military domain for the number and sophistication of customer requirements. This explains the trend of increased flight test duration. But who is deciding on the required flight test? Well, the design organization is asking for the test data to verify the design. Airworthiness is negotiating with the certification authorities, and salespeople are fixing the contracts with the customers. A very simplified depiction for the military aircraft market, but let us leave us at that. I think that this audience will easily agree when I say that the flight test organization usually are not involved in the activities that determine the amount of data to be gathered by flight testing. Well, with that, we as flight testers could say that the flight test organization is only fulfilling the requests of other departments. Please leave us alone with your requirements to reduce cost and time. Goodbye, have a nice day. And who did come up with the motto for the symposium? But do not get me wrong, I do not say that flight test organizations do not have any influence on the duration of flight test. There are variables we as flight testers can and have to optimize. The most obvious, and not by accident, the second part of this year's symposium's motto is flight test safety. A more cautious approach will take more time, more steps in the stepped approach, more analysis between flights, more inspections. But it's a commonplace in flight tests that the way to find out that flight test safety was reduced too much may be a very expensive one. Therefore, to go for a bold approach, for example, for engine envelope expansion, is a very risky approach and one I would never advocate. So if flight safety is no area of easy wins for flight test reduction, and if requirements are seldom getting less, is there something we can do? The answer for that is twofold in my eyes. We can work on deconflicting the flight test phase, bringing the maturation of parts of the new aircraft forward in time, and we can raise efficiency of the flight test effort. Now, when I say deconflicting the flight test phase, I mean to minimize the number of deficiencies that slip through the test process to be found as late as in flight test. Especially with highly integrated avionics suits and other complex systems, we much too often see undesired effects in flight the first time, causing late rework and therefore delaying cost for the overall development effort. To better understand and avoid the shortcomings of rig environments, it's important to reduce the number of such. To better understand and avoid the shortcomings of rig environments, it's important to reduce the number of such problems. And better collaboration between flight testers and rig testers may lead to better understanding of each other's ways of working. In addition, we have to find ways to bring complex systems in flight as early as possible. One of the interesting approaches of HR development is the idea of demonstrators. A demonstrator in flight test is a flying testbed for a strictly defined topic. They come in a lot of different flavors, like a testbed for highly integrated mission system, like the catbird for the F-35, UAVs with a safety pilot, aircraft with a mount for a test engine, aerodynamic demonstrators like the A340 blade demonstrator. There is a possibility to build prototype demonstrators for fly-offs like the YF-22 and YF-23 or the X-32, X-35. Other explains to test and demonstrate innovative concepts, podded solutions to carry sensors or communication systems, airplanes with variable stability, and so on and so on. The advantage of the testbed approach is that selected systems can be tested earlier in flight because there is no need to wait for the complete aircraft to be developed, produced, and certified. To prove something, you may not need all the refinements required for certification and customer readiness. There is one point which shall be taken to heart for demonstrators. It needs to have a closely defined scope from the beginning, and this scope has to be kept during the program. When set up correctly, a demonstrator obviously will cost some money, but it will reduce development risk considerably in a later phase. Besides other advantages like early customer involvement and other things. Back to the increase in efficiency. Basically, that comes down to combine test point of different disciplines and the use of gathered data more intensively. While I understand that this path is being heavily used in civilian programs already, I think there's still room for improvement in the military domain. Of course, a prerequisite for that is that in contrary to the testbed approach, the testbed aircraft must be in a configuration that allows using the same test point for several subsystems. That means the subsystems have to be in a final configuration. Maybe data mining techniques can help also, but I have the feeling that we use the data we have quite efficient already. Another area to increase test phase efficiency is to closely coordinate inspection intervals and upgrade phases to maximize test aircraft availability for flight. The key to high test efficiency is highly trained personnel. To combine test points from different disciplines, flight test engineers with a broad knowledge as well as specialists that concentrate on dedicated systems are required. Together, they have to cover in-depth knowledge of the systems as well as of physical basics of flight and broad knowledge of flight test methodology. Awareness of flight safety must be fostered by regular training, but equally important is a safety culture in which flight safety consciousness is appreciated and rewarded. Last but not least, flight test is a team effort, and every member of a flight test team must be capable to do that. The motivation aspect looks somehow marginalized on this slide, but only motivated people can keep up with the challenges on highly integrated and by its nature volatile flight test environments. A good basic engineering education and a tailored training on the job program to teach the particularities of the local flight test organization will give a new flight tester a good starting point. Training at test pilot schools is designed to teach a broad foundation of flight test methodology and processes. The graduates of these schools are the generalist flight test engineers that are needed to orchestrate combined flight test campaigns. A view over fence is also important to avoid organizational blindness. In addition to the test pilot school courses at universities, courses at universities can foster that. And even more important, attendance at flight safety events and symposia. As I said, even if online symposia may be convenient, an important value of a real-world symposium is missing in them. Personal contact and exchange with colleagues from other organizations and countries. Therefore, I hope that we will soon be able to have symposia that foster this exchange. Test management plays an important role. Besides creating an environment where flight safety and program desires are balanced the right way, management has to stay open to try out new ideas, even if the result is not always certain, program-wise, not with respect to safety. Due to the special nature of flight test management, management must be ready to give more responsibility to the test teams. And ideally, this is not only valid for the execution of a test flight, but also for planning and coordinating a larger test campaign. Because of the increasing time between programs I mentioned before, the opportunity to make experience in the new aircraft development program is rare. This affects some domains more than others. Ways have to be found to keep basic proficiency also for those disciplines not in action at a given moment, and to bring the relevant people up to speed again when their special knowledge is requested after some time. I know that it is difficult without a full-blown development program, but there are opportunities. For example, the already mentioned demonstrator programs could help, as well as participation in projects of external institutions like national research centers or in consultancy projects. And we have to use the facilities we have in new ways. Bringing flight testers to rig tests may add a more operational view earlier in the system test phase. As said before, maybe some flaws get detected earlier. And there are simulators we can use not only to keep proficiency for the test pilots, but also to train the whole test team, as well as to test out sequences of test points and rehearse them. Now let's come to the conclusions and the summary. Flight test of a large aircraft development will stay a large effort. So the way to reduce are limited. Flight test organizations have almost no influence on the required amount of flight data to be gathered. However, they can influence the structure of the flight test program. Saving at the expense of flight safety is definitely not recommended. The opportunities are to increase efficiency by coordination of system-wide test requirements and by minimizing downtime of test aircraft, to try to deconflict test phases by use of flying test beds and other demonstrators, and the key to an efficient and imaginative flight test organization are competent and motivated people. I hope you thought some of the thoughts being useful, and really invite you for comments. And sorry for the technical inconveniences.
Rudolf, don't worry about the technical inconvenience. It was worth it to stick through and see all the wonderful pictures of aircraft which you shared in your presentation. There were some very, very nice examples there. And obviously, speaking from Toulouse, I'm pleased that so many of them were Airbus commercial aircraft, but that's a very personal point of view. I had a question come in on the chat from Paul Cox, and he would like to know if you had any opinion on the use of scaled flight testing initiatives. Do you think those can bring some gains for our activity?
To be honest, even if I've heard some presentations on this topic, I have not made up my mind. I'm probably missing a little bit of the scientific background here. The point is, or my doubt is whether if you scale them big enough to have noteworthy cost savings, are they still close enough aerodynamically wise when you look at flight test, for example, at flight control demonstrators or scale demonstrators? So it's something to be considered, but I'm afraid I'm missing the background here.
I guess it's one of many different small contributions which could be made to the overall target of driving down length of campaigns or cost of campaigns. I don't think there's one single silver bullet which can magically solve the problem for us.
Definitely. This would be too easy.
Yeah, exactly. And then a lot of people would be out of a job if they suddenly had the magic answer, I'm sure. So. Okay, well, that was the only question, Rudolf. We had a nice comment from our colleagues in the India chapter, and I welcome them all to our conference today to thank you for your address. And it's true that one of the downsides of this format is that you can't hear the appreciation of the people who are joining. There is no clap function or cheer function. So, but you can see from the comments that people have enjoyed your presentation. So thank you very much for taking the time to speak to us today.
Thank you very much for giving me the opportunity, and I wish us all as pleasant as possible symposium. Thank you.